So some more differentiation of the exponential function, and specifically the chain rule applied to the exponential function e. And so we now know that the derivative of e to the x is e to the x. But if we want to apply the chain rule, the derivative of e to some function g of x, well, what are we going to get via the chain rule? Well, the chain rule is actually going to say that this is then going to be the derivative of the outer function, which is just going to be e raised to the g of x. But then it's going to be times the derivative of the inner function, where the inner function is g prime of x. And so in general, this is how we apply the chain rule to an exponential function. So now let's differentiate the following function. Alright, it can be helpful to recognize that this is really e raised to some g of x, where g of x is our inner function, and g of x is x squared plus 1 raised to the 1/2 power. Well, then if I want to find g prime of x, well, g prime of x, that's just a chain rule, so that's going to be 1/2 x squared plus 1 raised to the negative 1/2 times the derivative of the inner function, but that's just going to be 2x plus 0. So we found g prime. Well, then our outer function is e to the gx. So when I find y prime's then going to be e raised to the same thing it was before, that same g of x function, e to the square root of x squared plus 1, times g prime, where g prime is 1/2 of x squared plus 1 raised to the negative 1/2 times 2x. If we had some desire to clean it up a little bit, I could probably make it a little nicer to look at. I see that x squared plus 1 raised to the negative 1/2, that's really a square root in the denominator. And so I see this 2 over here, that's going to be 2 times the square root of x squared plus 1, all under 2x e to the square root of x squared plus 1, which will reduce a little bit further since 2 divided by 2 is 1. This is the exact same thing as x e to the square root of x squared plus 1, all divided by the square root of x squared plus 1. So if we wanted to clean it up a little bit, here we are. Alright, so now that we can take derivatives of the exponential functions with a base e, let's find the values of x at which the function has a possible relative maximum or minimum point. And then we're going to determine if there is a maximum or minimum. So recall that how do we do this? We use the first derivative test. So what's the first derivative test? The first derivative test says find the first derivative and set it equal to 0. So let's find f prime of x. Well, f prime of x here, notice that this is a product rule. So leave the second function alone. That's e to the 1 minus 2x times the derivative of 5x minus 2, but the derivative of 5x minus 2 is just 5 plus 0, plus leave the first function alone, so that's going to be 5x minus 2, times the derivative of e to the 1 minus 2x, well, that's a chain rule on e, or e to the 1 minus 2x, times the derivative of the inner function, which is just going to be negative 2, or 0 minus 2. And so then I have my first derivative. Well, then let's simplify all this, and then we're going to use set it equal to 0 to see which things occur. And so recognize what I did earlier. I factored out that entire e function, and I'm going to do that again. So that's going to be e to the 1 minus 2x times 5 plus negative 2. I'm going to go ahead and distribute this negative 2 into 5x minus 2. 5 plus negative 2 times 5x minus 2. And so let's clean it up a little further. That's e to the 1 minus 2x, 5 minus 10x, and I get that this is e to the 1 minus 2x times negative 10x plus 9. At this point, we should set it equal to 0 and use the zero product property. Alright, because first derivative test, right? Okay, zero product property says e to the 1 minus 2x equals 0, and negative 10x plus 9 is equal to 0. Now let's actually deal with e to the 1 minus 2x is equal to 0 problem. Since this is an equation, we should be able to solve this. Well, my claim is that if we recall the properties we talked about before, remember that an e raised to some x function will never be 0. It's not going to approach the x-axis. It's not going to cross the x-axis. Specifically, it approaches the x-axis because there's a horizontal asymptote there. And so this part right here has no solution. That's good for us. We don't have to worry about anything there. Well, then we just have to worry about this other part. So how about we subtract 9, negative 10x is equal to negative 9, divide by negative 10, divide by negative 10. We then get that x is equal to positive 9/10. Alright, so this is a location for possible extrema, right? We found our locations for possible extrema. That's at x equals 9/10. Now at this point, if we want to figure out what happens here, there's two good approaches. You could cut up the number line and check values on the left and right. But since we are talking about derivatives of exponential functions, I'm going to use the second derivative test to double check things. So let's do the second derivative test. I want to find f double prime of x. Well, f double prime of x is just going to be the derivative of e to the 1 minus 2x times negative 10x plus 9. So let's take the derivative of that. Well, let's leave the second function alone, just in the form of the way I've written it. That's going to be negative 10x plus 9 times the derivative of e to the 1 minus 2x. But the derivative of e to the 1 minus 2x is e to the 1 minus 2x times the derivative of the inner function, which is then negative 2. Then that's going to be plus, and sorry for the lack of space here, leave the first function alone, that's e to the 1 minus 2x, times the derivative of the second, but that's just going to be the derivative of negative 10x plus 9, or negative 10 plus 0. Well then, if you want, let's factor out that e to the 1 minus 2x again, and so that's all going to equal e to the 1 minus 2x times negative 10x plus 9 times negative 2 plus negative 10. I'm going to clean this up a little bit. F double prime of x is then going to be e to the 1 minus 2x times 20x times 20x minus 18 minus 10. Or simplify that a little further, e to the 1 minus 2x times 20x minus 28. So then, to confirm is this a maximum or a minimum, I can take f double prime of 9/10, f double prime of 9/10, but that's then going to be e to the 1 minus 2 times 9/10 times 20 times 9/10 minus 28, which I get to be approximately negative 4.5. But the fact that it's negative specifically tells me that this is a concave down function. And since it's a concave down function, it specifically tells me that at this possible extrema value that we found a moment ago, 9/10, this is a maximum. And so at x equals 9/10, there should be a maximum. Another large property of the e function, the exponential e function, is its relation to interest or increasing or decreasing value. And so here we have an example discussing an increasing value problem. And so a painting purchased in 2015 for $100,000 is estimated to be worth, in terms of a function, $100,000 times e to the t divided by 5 after t years. And so the question is at what rate will the painting be appreciating in 2020? And so specifically, this idea, at what rate will the painting be appreciating at in 2020, is really saying we should find the rate at which the value is changing. And so the rate of appreciating is the derivative evaluated at time t. And specifically, that is the first derivative, right? Because we're just talking about that rate of change. So if we want to figure this out, we need to find v prime of t. So what's v prime of t? Well, v prime of t, that's 100,000 times e to the t fifths. Well, the derivative of a constant times a function is the constant times the derivative of the function, and so that's going to remain 100,000. And then I have really just 1/5 t, so that's going to be e to the 1/5 t, or t over 5, but then the derivative of the inner function is just going to be 1/5. And so specifically, this is 100,000 divided by 5, or 20,000 times e to the t fifths. At this point, if I want to know what is v prime of t, where specifically we want to know what t is in 2020, well, the deal is that since the painting was bought initially in 2015, we do have to do a little bit of side work. Specifically, the time t that we're looking at is the final year. The t we're looking for is the final year 2020 minus 2015, so that's a change of 5 years, and so we're doing v prime of 5. And so v prime of 5 is then going to be 20,000 times e to the 5 over 5, or specifically, that's just 20,000 times e. Well, your calculator does have an e button, so that's 20,000 times raised to the first power, or approximately 54365.64, $54,365.64.